Greetings and salutations, everybody. This is Jacob. Okay, so how the heck do we go about solving this problem? Can't make heads or tails of it, you say. Well, if it makes you feel any better, my dude, this problem ran circles around me as well, or should I say semicircles. It ran circles around me until it didn't. I managed to crack it at some point. Persistence pays off, my friends. Oh yes. This is quite the problem though. It's no joke. You're gonna have to pull out all the stops to solve it, but it's not impossible. But if you haven't cracked it or just want to see the solution of it, that's why this video exists here, my friends. I'll walk you through it like there's no tomorrow. No one will leave this video scratching their heads. Oh no, not on my watch. So let's get right into it, shall we? So the problem is asking us to find the maximum angle the inclined plane can have before the semicircle starts slipping down or sliding down. Notice I say sliding and not rolling, as they're two different things in the statics and dynamics world. And the problem is also asking us to find this angle here, phi, when the semicircle is on the verge of sliding down the inclined plane. The phi angle is a little bit more involved to find, but rest assured, no one will leave this video still scratching their heads. Okay, so first things first, let's find the theta angle. We can't find phi without finding theta anyway, so we'll have to start with theta. So the first thing we'll do is break down the forces acting on the semi-cylinder into two components. The components parallel to the inclined plane and the components normal to the inclined plane, like we usually do in problems like these. So the forces acting on this semicircle are the friction force, the normal force N, and the weight of it itself, which is being applied to its center of mass. So the weight of the semicircle is m times g, and since the weight is normal to the ground, and this line is normal to the inclined plane, and this angle here is theta as well. So the x component of the weight, which is parallel to the inclined plane, is Wx equals m times g times sine of theta, and W of y is m times g times cosine of theta, which is normal to the inclined plane. So the net forces on the x-axis and the y-axis have to be zero, obviously, when the semicircle starts sliding down, or is on the verge of doing so. So the net forces on the x-axis are zero, so we have W of x minus F of s equals zero, and the net forces on the y-axis are zero, so N minus W of y equals zero. Further, when the semicircle is on the verge of sliding down, then the static friction force is at its maximum, which is F of s equals mu of s times N. And mu of s is the coefficient of the static friction, which is 0.3 from our initial conditions. So now we have Wx minus mu of s times n equals 0 in our first equation. We solve for n in our second equation, and we get n equals m times g times cosine of theta. And we plug that in our first equation, and we get m times g times sine of theta minus 0.3 times m times g times cosine of theta equals 0, which is m times g times sine of theta equals 0.3 times m times g times cosine of theta. And the mg's cancel out, and we get tangent of theta equals 0.3, which is theta equals arctangent of 0.3, which is 16.7 degrees. One down, one to go. So the easy part of the video is over. Now is where the rubber meets the road. Now comes the hard part, my friends. We have to find the angle phi, which is no small feat. Oh yes. So brace yourselves, my friends. So before proceeding any further, we're going to have to actually find where the center of mass of the semicircle is. If you recall from your statics and dynamics class at college, if you've taken one, that is, there was a certain formula you used to find the centroid of an area under the curve of a homogeneous mass of a constant density, of course. This is the formula here. X over bar equals the ratio of these two integrals, where squiggly x is the x component of the center of mass of the differential element, and d of a is the area of the differential element. The differential element is a very small element of area that we integrate over the entire area under the curve. The small area is usually a triangle or a rectangle. Don't worry if you don't understand this formula just yet. you'll understand it as we use it as an example on our semicircle. So we'll use the formula to find the center of mass for the semicircle, but we won't be using Cartesian coordinate system here. We'll use polar coordinates in this case, as they lend themselves well to circles and semicircles. If you don't remember from Calc 2 or Calc 3 what polar coordinates are, in polar coordinates, instead of using x and y, we use r and theta, r being the distance of point from the point of origin, and theta is the angle between the x-axis and the line segment that connects our point to the point of origin. So r is being used in place of x and theta in place of y. So we have our semicircle here situated on our polar coordinate system from r to negative r, and from theta equals 0 to theta equals pi. We'll use a very small circle sector. Do you recall the area of a circle sector? It's r squared over 2 times theta, where theta is in radians. Our elemental area is d of a equals r squared over 2 times d theta, which is a very small angle here. And since this is a very small sector, then it's virtually indistinguishable from being a triangle. And the center of mass for a triangle is known. It's located at 1/3 of its height. So since the height of this triangle is r, and the center of mass is located r over 3 distance from its base, this small side is its base, then the center of mass is located 2 times r over 3 distance from the point of origin. Now we'll put squiggly x and squiggly y in terms of r and theta using trigonometry, and we have squiggly x equals 2 over 3 times r times cosine of theta, and squiggly y equals 2 over 3 times r times sine of theta. And we plug these values in our center of mass formula, and we get x over bar equals diff integral of 0 to pi of 2 over 3 times r times cosine of theta times r squared over 2 d theta over a definite integral of 0 to pi of r squared over 2 d theta. The r squared over 2 come out of the integrals, and they cancel out from the numerator and the denominator, and we take out the 2 over 3 times r out of the integral of the numerator as well, and we get 2 over 3 times r of the ratio of these two definite integrals, and we do the integration and the algebraic operations, and we get x over bar equals 0, and y over bar is 4 times r over 3 times pi. So we found the center of mass for the semicircle. Okay, so now what do we do? The age-old question. Oh yes. So in order for the semi-cylinder to not start rolling, then the net torque on it has to be 0, or net moment. The moment of a force provides a body with a tendency to rotate about a fixed axis or point. So if this circle starts rolling, for example, then where would that point be? It would start rotating about this point here, correct? The center of the whole circle, the midpoint of the semicircle's flat side. It would rotate around this point if it were to start rolling. So in order for it to not roll, the net torque on this point has to be 0. So what are the forces that contribute toward the moment about point O? One of them is the static friction, and the static friction is mu of s times n when the semicircle is on the verge of slipping. So the moment of this force about O is F of s times r, where r is the distance from point O, which is the radius of the semicircle. So that's one force. The other two forces that contribute to the torque are W of x and W of y. So the moment of W of x is W of x times the distance of the center of mass of the semicircle from point O, right? Nope, not quite right. The latter part of the product is correct, but not the former. W of x has to be parallel to the flat side of the semicircle, but it's not, as we see here. So we have to break it down into further components, one of which is parallel to the flat side, and the other one doesn't contribute, and it's perpendicular to the flat side. This is where the angle phi comes in. Oh yes. So let's turn our attention to this diagram here. Since this line is parallel to this, and this line is parallel to this one, and this angle here is phi as well. Likewise, since these two pairs of lines are parallel, then this angle here is theta as well. And so this angle here is phi minus theta, and this angle here is phi minus theta as well. And this is W of x, and this force here is parallel to the flat side of the semicircle, which is the force we're looking for. We'll just call it W1. So we have cosine of phi minus theta equals W1 over Wx, which is W1 equals Wx times cosine of phi minus theta. And the moment of this force is Wx times cosine of phi minus theta times 4r over 3 times pi. 2 down, 1 to go. So now we have to find the component of Wy that contributes to the torque of the semicircle. So we have to find the angle of this component makes with this line here, which is perpendicular to the flat side of the semicylinder. Since this line is perpendicular to the flat side of the semicylinder, and this total force is perpendicular to this line, and this angle here is phi as well, and this angle is phi minus theta as well. And so we have sine of phi minus theta equals W of 2 over Wy, which is W2 equals Wy times sine of phi minus theta. And so the moment about O of this force is W of y times sine of phi minus theta times 4 times r over 3 times pi. So putting this all together, since the net torque has to be 0 about O, we take the moment of the friction force as positive, going counterclockwise, and the other two moments are going in the opposite direction, clockwise. So we take them as negative. Doesn't matter which ones we take positive or negative, as long as we're consistent. So now we have mu of s times n times r minus w of x times cosine of phi minus theta times 4r over 3 pi minus w of y times sine of phi minus theta times 4r over 3 pi equals 0. And we plug in all our values that we found when we answered the first question and from our initial conditions, and we get 0.3 times m times g times cosine of 16.7 times r minus m times g times sine of 16.7 times cosine of phi minus 16.7 times 4r over 3 pi minus m times g times cosine of 16.7 times sine of phi minus 16.7 times 4r over 3 pi equals 0. Now we use our trigonometric identities for the difference of two angles. Here they are. And after factoring out m times g times r from the equation, bringing the last two terms to the other side and evaluating sine of 16.7 and cosine of 16.7, we have 0.287 equals 0.406 times 0.95 times sine of phi minus 0.287 times cosine of phi plus 0.122 times 0.957 cosine of phi plus 0.287 times sine of phi. And we do the calculations and all the algebraic operations. The cosine of phi's cancel out. And we solve for phi, and we get phi equals arcsine of 0.678, which is approximately 42.6 degrees. And that's curtains, my friends. That's your answer. 42.6 degrees. Should I color you surprised, or was that what you expected, my friend? So that's the phi angle when the semicircle is on the verge of slipping down the inclined plane, my friends. Oh yes. Wow. Just wow, you guys. What a problem. Quite a specimen of a problem, is it not? That phi angle didn't give up its secrets willingly, did it? But we're no strangers to hard work here on this channel. Such things don't deter us. Oh no. We don't back down from a challenge. We roll with the punches, as they say. This was quite a problem, and I found it in a textbook, believe it or not. Sometimes I'll find puzzle-like problems in a textbook. Oh yes. I'm a sucker for a good semi-cylinder problem. This is the second semi-cylinder problem in a row that I'm making as a physics category. Statics and dynamics in general lend themselves well to puzzles, and mechanics in general. You know, I was originally going to post a thermodynamics problem for this video, but I scrapped the idea, even though thermodynamics is interesting in its own right, but it's not really suited for puzzles, unfortunately. The problem I was working on had too much of a feel of an exercise from a textbook, so I scrapped it and went with the tried and tested category of statics and dynamics. You can never go wrong with that category. Most of the physics puzzles you'll see on this channel will be on mechanics. Occasionally I might dabble into other fields like electrical circuits and thermo, but very sparingly. There's such a thing as spreading yourself too thin, my friends. I mean, this is a puzzle channel, not a physics one, but thermo's a more interesting category as a differential equations video, so I might use thermo in a differential equations video. So that's pretty much it. Smash those buttons like there's no tomorrow. Let me know down below in the comments if you like this puzzle, if you solved it another way. Keep the suggestions coming, as always, my dudes and dudettes. And I'll see you guys in the next video. Bye-bye.